Hello, this is your host Amitkeerti and welcome to the discussion on deep learning. In this video, we will discuss on applying artificial neural networks to the Internet Movie Database, that is IMDB Dataset. IMDB Dataset analysis is a classification problem. The intent is to classify a review as being positive or negative for a movie. As a part of the IMDB dataset analysis, we'll look at the following topics. First, we will implement an artificial neural network model using Keras and analyze the results. Then we will analyze the impact of size and shape of the neural network on the model. Then we will analyze the impact of regularization. Following which, we will analyze the impact of optimization. We will then analyze the impact of activation functions, following which we will analyze the impact of initialization. And finally, we will analyze the impact of batch normalization. Before we start building the artificial neural network and optimize it, let us look at some basic details of the IMDB dataset. It is a dataset of 50,000 movie reviews. These are split into train and test sets as follows. 25,000 reviews are part of the training set. 25,000 reviews are part of the test set. Out of all these reviews, 50% are positive reviews and 50% of them are negative reviews. The entire dataset is packaged as a part of Keras. These reviews have been pre-processed by converting words in each review to a set of integers. Let us start by building a model for the classification problem. We will use Keras to build the model. We start off by loading the IMDB dataset. Each of the reviews would be of different size, hence we limit ourselves to the top 10,000 frequently occurring words of each review. Since the dataset has been pre-processed, we get the train and test dataset in separate vectors. I have printed the first review from the dataset. Each number represents one word from the first review. Now each review is of different size, and the face value of numbers that represent the words in the review do not have any meaning. So we need to do a one-hot encoding of all the reviews. We do this by creating a matrix of size equal to the number of reviews in the set by the number of maximum words. In case of the training set, this would be a matrix of 25,000 rows by 10,000 columns. The words which are present in the review are marked as 1 in the matrix and rest of the words remain as zeros. This one-hot encoding is done for both the training and test set. We now create a 3-layer artificial neural network. The first 2 layers have 32 neurons and the last layer has 1 neuron which outputs whether the review is positive or negative. We use rectified linear unit, that is ReLU, activation for the input and hidden layer, and at the output layer we use the sigmoid activation function. Now the training data comprises of 25,000 samples that is being split into training set of 20,000 samples and validation set of 5,000 samples. The model will learn from the training set samples and subsequently we will fine-tune it using the validation set of 5,000 samples. We now configure the model for training. We use the optimizer as RMS prop. An optimizer's job is to update the weights and bias of each layer so that the model slides down the paths towards the minima. RMS prop adjusts the weights in a 2-step process. In the first step, we accumulate via the parameter S the element-wise square of gradients, which are multiplied by the exponential decay parameter. Then we do an element-wise division of the gradient with the accumulated parameter, and the resulting value is subtracted from the weights to get the new weights. These are the first 2 equations that we see there. The learning rate was set to 0.001 in the above case, and exponential decay, that is beta, was set to 0.9. The second parameter to the model.compile function is the loss function. We set the loss function in this case to binary cross entropy or a log loss function. A loss function computes the total loss experienced in the model based on the current values of the network parameters, that is weights and bias. Here p hat of I should be the output of the sigmoid function. If the computed value from the network, that is p hat of I, is close to 1 and the actual value, that is y, is also 1, then it means we have accurately predicted the output, so the loss will be 0. Else we do not compute the value properly and hence the value would be a large number. So binary cross entropy provides a real number as a loss value. Our aim is to minimize this loss by iteratively modifying the weights using the RMS prop optimizer. The model definition is ready, and now we have our model to learn from the training set. The model learns from the training set of 20,000 instances across 25 epochs in batch size of 512 instances. At each epoch, we evaluate the learning using the validation sample comprising of 5,000 samples. The graph on the left-hand side shows the training and validation loss. We can clearly see that there is a divergence in the result between training and validation set. The model has lower loss on training set, but the loss keep increasing when the validation set is introduced. This is a clear indication that the model has overfit the training set. This is further confirmed from the accuracy values for training and validation set. The accuracy on the training set is close to 1, whereas in case of validation set, the accuracy is close to 86%. The best way to reduce overfitting is to perform regularization. But before we regularize, let us check the impact of increasing the hidden layer count as well as increasing the neurons in each layer. Let us try to check the performance of the model by changing the number of hidden layers and by changing the number of neurons in hidden layers on the IMDB dataset. We start off by increasing the number of hidden layers. When you have fewer hidden layers, we are implying that we can solve the problem using simpler functions like linearly separable functions. And when we add more layers, then we are stating that the input data cannot be learned in a lower dimension space, and we need to go to a higher dimension space, like fitting a higher order polynomial. For the model that we are developing for IMDB dataset, when we increase the number of hidden layers to 2 or 3, there is no marked improvement. The results show that the model still overfits the training sample. By the way, in a widely cited IEEE paper from 1987 by Lipman titled An Introduction to Computing with Neural Networks, the author concludes that for most problems, a 3-layered network is more than sufficient. Since there was no gain by adding more layers, we switched back to a network with one hidden layer and increased the number of neurons to 128 in both the input layer and hidden layer. Even with the increase in the number of neurons, overfitting is still observed and there is no change in the results. Overfitting is a problem that can be solved by regularization. Regularization is a method of regulating the network parameters. By using regularization, we either reduce the magnitude of the parameters or we eliminate some of the parameters. This should reduce the overfitting being observed on the dataset. L1 regularization is similar to lasso regularization from linear regression. L1 regularization mitigates overfitting by making some of the parameters to 0. Hence, in case of L1 regularization, weights for some of the connections may become 0 and we get a sparse model. L1 regularization is implemented by adding an additional term to the cost function, which is sum of absolute value of the weights. The quantum of addition is governed by the hyperparameter alpha. The graph shows that the loss as well as accuracy values for training and validation set of our IMDB dataset. The hyperparameter alpha is set to 0.001. Overfitting has reduced because the model has now seen many of the weights of the connections to 0. So by regularization or using L1 regularization, we see much better results. Let us now move on to L2 regularization. L2 regularization is similar to ridge regression from the linear regression. L2 regularization mitigates overfitting by reducing the quantum of weights. It does not make the weights to 0 though. L2 regularization is implemented by adding an additional term to the cost function, which is sum of squares of weights reduced by half. The quantum of addition is governed by the hyperparameter alpha. When L2 regularization is applied to the IMDB dataset, the quantum of loss, as shown in the graph on the left, has reduced compared to L1 regularization. However, both the validation loss and validation accuracy drift from the training data, which indicates that the problem of overfitting still persists. Note that alpha was set to 0.001. If alpha is changed to a bigger value, say 0.1, then one can observe a reduction in overfitting, but at the same time there is a drop in accuracy. Even though overfitting could not be reduced by using L2 regularization, there is one positive aspect of L2 regularization compared to L1. We can see from the loss graph that the quantum of loss has come down noticeably. In case of L1 regularization, for the validation set, the quantum of loss after 25 epochs was 0.65, whereas in case of L2, the quantum of loss is 0.45. In addition to L1 and L2 regularization, there is another regularization which is a mixture of both L1 and L2. This is similar to elastic net, which is part of linear regression. The equation above shows both the terms of L1 and L2 being added to the cost function. An additional term R has been added to control the contribution of L1 and L2 to the overall cost function. When L1 L2 regularization was applied to the IMDB dataset, we see that the results are much better than both L1 and L2. The overfitting is further reduced and the training and validation loss as well as accuracy are close to each other. Dropout is another method of regularization. It is a counterintuitive and interesting method of regularizing the data. In this method, the model will randomly drop some of the neurons from the network. So in round 1 of training, on a batch we might have 75 neurons, and for the next batch we might have 60 neurons. Since the selection of neurons is random as well, we could end up with entirely new network for each round. This is like an ensemble learning, where in each round the batch of instances are exposed to a different neural network. Dropout emulates this ensemble learning concept. When dropout was applied to the IMDB dataset at both the input layer as well as hidden layer, and the dropout rate was set to 0.5, we observed 3 interesting results. Number 1, the overfitting gets substantially reduced. Number 2, the loss gets reduced compared to L1 and or L2 regularization. And number 3, the accuracy reached close to 90%. Early dropping is another type of regularization, wherein the learning is stopped at the epoch where the loss was minimal or accuracy was at its highest. The parameters learnt at this epoch are then used for prediction on the test data. This concludes our test on different regularization techniques. We saw multiple regularization techniques. Among all the regularization techniques, dropout produced the best results with loss of about 0.27 and accuracy close to 90% on the validation set. Let us now turn our attention to optimizers. Gradient descent is the most popular optimizer function that is studied as well as used in many problems. Gradient descent updates the weight theta by subtracting the gradient of the cost function with respect to the weight. Researchers have proposed many enhanced optimizers. In all our previous results, we used RMS prop as the optimizer. In this section, we explore other optimizers to check their applicability to the IMDB dataset. Momentum optimizer, proposed by Boris Polyak in the year 1964, provides an enhancement to the plain vanilla gradient descent. In gradient descent, the slide down the slope is achieved by taking small regular steps. Gradient descent merely subtracts the gradients which is governed by the learning rate. It does not keep an account on the previous gradient. Momentum optimizer, on the other hand, proposes to speed up the gradient descent by taking faster steps during the descent. This is achieved by remembering the previous gradients in a momentum vector m. At each iteration, it adds the local gradient to this momentum vector m, which is multiplied by the learning rate. This momentum vector is then subtracted from the weights to get the updated weights. So as iterations increase, the quantum of momentum vector increases and the weight adjustments are higher. Hence the name momentum optimizer. To keep a check on momentum vector from growing very large, it is multiplied by a hyperparameter beta, which is simply called as momentum. When the momentum optimizer was applied to the IMDB dataset, we noticed that the training sample was being underfit. So dropout rate was reduced from 50% to 35%. When we reduced to 35% and then we tried again, the graphs show the results. The loss and accuracy graphs indicate that there was no major improvement seen due to momentum optimizer in comparison with RMS prop optimizer. Let us now move on to Nesterov optimizer. Nesterov optimizer was proposed by Yuri Nesterov in the year 1983. Nesterov optimizer provides an enhancement to the momentum optimizer. Instead of accumulating the gradient of the weights computed at local position, Nesterov accelerated gradient proposes to accumulate the gradients at a position that is slightly ahead in the direction of momentum. In the equation, we see that the gradient is not computed at the current location theta, but at a location of theta plus beta m, which is in the direction of momentum. The resulting momentum is then subtracted from the weights to get the updated weights. Nesterov accelerated gradient marches towards the minimum at a faster rate compared to momentum optimizer. When Nesterov optimizer was applied to IMDB dataset, no additional improvement can be seen in comparison to RMS prop or momentum optimizer. ADAM, which stands for Adaptive Moment Estimation, combines the concept from momentum optimizer as well as RMS prop optimization. The equations are a little involved. Let us look at them in detail. Let us concentrate on equation 1, 2 and 4 for now. Equation 3 merely helps to boost the value of m and s at the beginning of the training when these values are biased towards 0. Now equation 1 computes the exponentially decaying average of the past gradients, similar to the way momentum optimizer computes this value. Equation 2 computes the exponentially decaying average of square of the gradients, which is similar to the way RMS prop computes s. Now equation 4 proposes to compute the new weights using the momentum vector m and the vector s. The new weights are computed by subtracting the ratio of m and square root of s. The division is an element-wise division, and the epsilon is a smoothing factor to avoid the divide by 0 scenario. To understand this further, let us take a scenario where the ith gradient is a large value. In equation 1, this is multiplied by 1 minus 0.9. That is, a large gradient is being multiplied by 0.1. This reduces the impact of large gradient to some extent. This resulting value is then accumulated as a part of vector m. When many such large gradients from the mini batch are accumulated for the ith element in the vector m, the ith element in vector m will have a substantial value. Now as a part of equation 2, the same large gradient undergoes element-wise squaring, thereby generating an even larger value. But it gets smoothened because it gets multiplied by a much smaller value 0.001 because beta 2 is 0.999. Now this value gets accumulated as a part of S. In equation 4, we subtract the value obtained after element-wise division of m with square root of S. Since m will be a larger value compared to S, the resulting term that will be subtracted will end up being a higher value. This value is subtracted from the weights to get the updated weights. When ADAM optimization was applied on IMDB dataset, the dropout had to be increased to 55% to avoid overfitting. The results are not dramatically different from RMS prop. The advantage was seen in the convergence of results between training and validation set. Both the loss and accuracy converged towards the 25th epoch. Hence, among all optimizers, ADAM optimizer is the best suited optimizer for IMDB dataset. Let us now move on to the activation functions. An activation function of a node defines the output of a node for a given set of inputs to the node. An activation function takes an input, then computes y is equal to theta m plus b, that is the dot product of weight and the input vector added with the bias vector. It then generates the output vector of activation function for all the neurons. Till now we have been using rectified linear unit for the hidden layers and the sigmoid function for the outer layer. We will evaluate if activation functions have an impact on the performance of the model. ReLU activation function generates an output which is a replica of the input, provided the input given to it is greater than 0. However, if the input given to ReLU activation function is less than 0 or equal to 0, then ReLU clips and generates a 0 as its output. If a neuron outputs 0, it is as good as there is no output from the neuron, which means the neuron did not fire. The graph on the top right hand corner shows the output of ReLU activation function for different values of input. Now one would be curious to know as to what is the input to an activation function. The input to an activation function is the term y, which in turn would be sum of the product of weights and input neuron with the bias. The results that we have seen till now for IMDB dataset have been with the ReLU activation function itself for the hidden layer and the sigmoid activation function for the output layer. The graph shown here are the results which are the exact replica of the results that we saw for ADAM optimizer. ReLU suffers from a problem called dying ReLUs. During the training process, some of the neurons die. That is, once they start to output 0, they never recover and constantly produce a 0. The gradient descent will not revive it back. To overcome this problem, an enhancement to ReLU was proposed wherein the output of the activation function will not be 0 when y is less than or equal to 0. Instead, it will be a small value governed by the term alpha. This ensures that the output is never 0 and the neurons do not die. When leaky ReLU was applied to IMDB dataset, there was no additional benefit seen on top of the results we observed for ReLU. The results are captured in the graphs at the bottom. ELU is another variation of ReLU wherein for negative values of y, the exponent of y is taken to compute the output. It is multiplied by alpha, which governs the magnitude of the output. The graph on the top right corner shows the behavior of ELU activation function. Specifically, you can concentrate on the values when the independent variable is less than 0. We can see that for negative inputs, the output of the activation function is an exponential value. When ELU was applied to the IMDB dataset, there was no additional benefit seen on top of the results that we observed for ReLU. The results are captured in the graph. The activation functions that we have seen till now, that is ReLU, leaky ReLU or ELU, were applied to the hidden layers, where we expect a non-binary output. On the other hand, at the output layer, we expect the activation function to provide a binary response. In all our previous runs, we used a sigmoid function, which provides a logistic regression output, that is 1 by 1 plus e raised to minus y. There are other activation functions that can provide a similar response, which can then be interpreted as a binary output. One such function is tan hyperbolic function. The graph on the top right hand side shows the expected output for tan hyperbolic for different class inputs. Point to note that it saturates on either side for larger values of independent variable, which is helpful for binary classification problem like the IMDB dataset that we have. The reason why it saturates is because of the addition of the two exponential terms in the denominator, which is always a positive value. So denominator will always be higher than numerator. So you cannot go beyond 1 in either direction when you have a tan hyperbolic activation function. When tan hyperbolic activation function is applied at the output layer to IMDB dataset, there was no marked improvement in the results compared to the results for sigmoid function. Now deep learning libraries like TensorFlow and hence Keras have many other activation functions like linear, hard sigmoid, SELU, soft plus, soft sine, etc. One can explore these activation functions as well. However, we stop our exploration of activation functions and conclude that ReLU is sufficient for the problem at hand. One of the interesting items that goes unnoticed is the parameter initialization. When we begin training, the parameters of the neural network, they need to be set to some default value. Parameter initialization is the process of setting the default value to these network parameters, that is weights and bias. Appropriate initialization of the parameters can speed up the learning process and we avoid the problem of exploding or vanishing gradients. Let us assume that we have initialized the network parameters to large values. When the input data is multiplied by these large values, the result in logits that are larger. And when these logits are input to the activation function, like the sigmoid or tan hyperbolic, they will start to saturate. Once they start to saturate and the gradients that are generated would be very small. When these smaller gradients are backpropagated, the learning that each neuron undergoes would be very, very small, which would lead to slower learning, and we would end up with longer learning cycles spanning multiple epochs. In case of IMDB dataset, we have not seen this happen because by default, Keras uses GLOROT or Xavier initialization, and slow learning does not seem to be a problem. We will nevertheless try to understand the impact of parameter initialization. By default, Keras initializes the parameters using Xavier or GLOROT initialization. It's the name of a same person, Xavier GLOROT. The code on the bottom left hand side shows the code for dense class for Keras.layers, where we can see that by default the kernel is initialized with GLOROT uniform. Now what exactly does uniform mean here? There are two ways in which the weights could be distributed. If the kernel or weights have a normal distribution, then the mean would be 0 with a standard deviation of square root of 2 over sum of fan in and fan out. However, if the kernel or weights have a uniform distribution within a range of -r to +r, then the standard deviation would be square root of 6 over sum of fan in and fan out. The graph on the right hand side shows the results of IMDB dataset when the kernel is initialized using the default GLOROT uniform. These are the same results that we saw when we analyzed Adam Optimizer. HE initialization. The other initialization function that is widely used is called the HE initialization. HE refers to the name of the author who proposed this initialization method. HE initialization is generally used when the activation function used is ReLU or one of its variants like ELU. When we applied the HE initialization to the hidden layers of the model for IMDB dataset, and when we simultaneously applied the GLOROT initialization to the output layer with tan hyperbolic as the activation function, there was no additional improvement seen in either the loss or the accuracy of the model. Hence, initialization is not going to help improve the accuracy or loss of the model. Let us now move on to another interesting concept called batch normalization. An activation function like ReLU has no upper bound on the values that it outputs. Now during training, the network parameters keep varying. This can sometimes result in large values generated by activation functions, which we call as activation explosion. In a deep neural network with multiple layers, this activation explosion will then result in subsequent layers receiving large input values, which can destabilize the gradient descent. So each layer would need to adjust to new distributions at each training step. This is called as internal covariance shift. Hence there is a need to correct all activations to be zero mean and of unit standard deviation, so that all the layers see a normal distribution of the inputs across multiple batches. In short, at input layer we generally ensure that the features are scaled by using, say, a standard scalar. The same scaling process needs to be done to the inputs of hidden layer. Batch normalization takes care of exactly doing this, that is, scaling the inputs from hidden layers which go into the next layer. Note that batch normalization can be done just before the activation function of a layer or immediately after the activation function of the layer. The original paper that proposed batch normalization proposes to do this just before the activation function. Batch normalization is generally achieved by computing the mean and standard deviation on a per batch basis and adjusting the inputs using this mean and standard deviation. The first equation of batch normalization computes the empirical mean of the mini batch. For example, if the mini batch have 5 instances and the first parameter of these 5 instances had the values 1, 2, 3, 4 and 5, then the mean would be 3. The second equation computes the standard deviation, that is, how far are the values from the mean. So for the same set of numbers, the standard deviation turns out to be 2. The third equation uses the computed mean and standard deviation to shift all the values around the mean. Hence equation 3 computes the zero-centered and normalized values. For our 5 numbers, these numbers values that are zero-centered would be minus 1.414, minus 0.707, 0, 0.707 and 1.414. The final equation helps us to scale and shift these normalized values to a different set of values. This could optionally be done based on the specific requirements of each layer. Now batch normalization in Keras provides an additional parameter called the momentum parameter. This parameter indicates how much statistics of the previous batch should be considered during the current computation. If momentum is set to 0, then only the statistics of current mini batch are considered. Generally, a higher value like 0.99 is set for momentum parameter. When batch normalization was applied to IMDB dataset, the results did not improve. In fact, there was a degradation seen in both the accuracy as well as the loss. Changing the momentum to either 0 or 0.99 did not seem to make any improvement. Before we end the discussion, let us summarize our findings. The summary is divided into 2 sections. The section on the left provides the preferred options for the different optimization and tweak that we have looked at. The section on the right hand side shows the recommended model for the IMDB dataset that aids in classifying the movie reviews. The recommended model generates an accuracy up to 89% with a loss of 0.27 or thereabouts for both the training set and validation set. This concludes the discussion on IMDB Dataset. Thanks for watching.